Okay, so 2 weeks ago, so last week there were no class. So 2 weeks ago we started the section 12, comparing the triangular prism equation and the Pentagon equation. Because we will use the notation and result in section 11, which is very short, let me briefly recall the notation from this section, and also because it was 2 weeks ago. So in section 11, we was about Pentagon equation. So we consider element of the basis. So we consider basis element of this Hom space. Each element of this Hom space is denoted like that. And each morphism in this Hom space, alpha, can be pictorially represented by such a trivalent vertex, I, J, K, for I, J, K, like that. Okay. To state the Pentagon equation, we will need to define what is the F symbol. So the F symbol depends on 6 indices for the object and 4 indices for the morphism. In fact, only the morphism are required because the morphism contains in itself the object, like that. So you define the F symbol. So the F symbol is denoted like that, and it is defined such that so you have a morphism like that, such a composition. It can be written, it can be decomposed like that, with this basis here, which pictorially can be written like that. So you have this morphism, a composition like that, and you can write it as a linear sum of such morphism with this coefficient. Okay, and there is this is well defined. There is a unique way to do that, and so that the data of this and this provide exactly this number, which is called the F symbol. And so now, what is the Pentagon equation? So the Pentagon equation is you replace, so you have this pentagon of this five picture like that. So you have 2 ways to go from here to here. This one way and another way. These 2 ways can be formulated as an equality. Each path like that correspond to such. For example, here you move from here to here, and so you get an equality of F symbol called the equation 14. So we will in the next section we will use the equation 14 several times. I will refer to this equation, and with the good the good morphism in the good space, Hom space, etc. Okay. So in this section we started last time, we will see that in fact the Pentagon equation as it is written here can be interpreted as a triangular prism equation of specific configuration. And by specific configuration, I mean a specific labeling of the triangular prism. So the triangular prism equation is 2 ways to develop the triangular prism with some specific label called the reference pattern. If you change the labeling a bit, then you get another configuration, which we will call the Pentagon equation configuration. And this variation in the labeling will be proved by can be reinterpreted as a change of basis, as we will see in section 12. Okay, so we keep the notation from section 10.1, so it's quite far. Let me check what I am talking about. Oh, this is something I read last 2 weeks ago, but so notation 10.1 is the simple object of the fusion category will be noted xi up to isomorphism. X1 is a unit. The dimension of the home space between xi tensor xj to xk will be noted nijk. An object x is self-dual if it is equal to its dual, x equal x star. And the labeling by an object xi will be simplified by just the index I. And the dimension of xi will be noted di or dxi. So this is what I mean by notation 10.1. Okay. So as I said, we will show that these two are equal up to a change of basis. And I note here that, in fact, this section can be considered as independent of in the paper, independent because in the sense that it will not be used. So the section 13 and 14 will not use this section, but it will be used in the future when you need to consider categorification, because all what we did before, all what we apply in this paper is applying the localization strategy as a categorification criterion, and more precisely here, it was applied to exclude. So when you want to exclude, you don't need to have the full system. As long as you have a local subsystem which has no solution, it's enough. And when you want to categorify, you want to make sure that a solution of that will provide a solution of that. That's why when you want to categorify, you really need the correspondence between the two. And in the future paper, which is in progress about near group category, we will need this correspondence. Okay, so definition. So the goal of this section is to prove this correspondence. And in fact, we will start from this Pentagon equation, and we will see how. So you already have a picture here. And in fact, the idea is that if you, this number, if you take this number can be considered as the inner product of this one and this one. The inner product, you take this one, you put it here, you reverse, you put it here, and then you take the trace. What you get is isotopic to something like that, a tetrahedron. So this is, and we can reinterpret the tetrahedron with the monoidal tetrahedron, etc. So the idea is that you can recover the triangular prism equation from that. And we will see in details how to. So we need some preliminary definition, and we will explain that in full details. Okay, so okay, so let's come back to monoidal category. So let's see, be a monoidal category. Category with left dual. So in this definition, we will just, in fact, we will just define, in this definition, we will just define natural transformation to replace a morphism written like that by a morphism written like that. You just need, in fact, to move it like that. So we will define natural transformation to do that. This is the only goal of this definition. But because we want to do it very cleanly, we do it as follows. So let mu monoidal category be dual. Let Fg be functors from C cube to the category set. Define, as we in fact already we already used this trick before, define as a composition of usual functors such that, etc. So define as the composition of usual functor such that f of x, y, z is OMC x tensor y z and g of x, y, z is home space 1 z tensor y star tensor x star. And x, y, z are objects in C. For all x, y, z in C. Okay, so this is the morphism here are of this form. The morphism here are of this form. So to go from one to the other, you just need to do something like that. And this will be the natural transformation. We will define now. So consider the natural transformation. So transforming mu into mu tilde, morphism mu to morphism mu tilde from F to G. Remember that the natural transformation is a map from a functor to a functor. Define. So yeah. So natural transformation is from that to that. But then you can define it pointwise from an element here to an element here. But the natural transformation is really here. Defined as defined by so mu tilde equal mu. So you have element of the home space like that, x, y, z. And as I said, you are doing something like that. So I need more space here. This one. Okay. Okay, so you do that and you do that. And now you have here y star, x star. Okay. So nothing complicated. So this is, it is a natural isomorphism. So anyway, don't need to go into too much details here. So by applying the natural I-junction isomorphism, natural I-junction isomorphism, Egno book proposition 2.10.8. And the inverse, like that, mu equal mu star, like that, z here. Okay. X and Y. Okay. So this is a natural isomorphism. So yeah, we already do something similar before. No problem. So how? So we will use this natural transformation to reformulate first equation 13 and then equation 14. So we will reformulate. So this mu1 is something of this form. So using the previous natural transformation, you can reformulate it with something of this form. So let me explain how to reformulate equation 13 like that. Now let us reformulate equation 13 using above natural isomorphism. Isomorphism as follows. So you have mu1, mu2. The composition of mu1 and mu2. So the point is the following. This mu1, sorry, mu1 is like that. And you have mu tilde, mu1 tilde is like that. So if you do that, this is equal to mu1. So you can replace mu1 here by that. You can do the same here, and you get the following. You get the following. So mu2. Okay, so let me put some color. So mu2 tilde, mu1 tilde. You get something exactly like that. So tac, tac, tac. And you start to see some pattern we saw before. And this one here, like that. So let me put this color maybe. I5, I3 here, I1, I2, I4. So let me come back a bit, or let me, maybe I will copy this here, and I will erase it. So that I don't have to come back third time. Copy. Okay, so let me put it here. This is the equation 13. So I will keep it here. It's much more convenient. So this one here. Sorry. So this is equation 13. I just copy as before. And now you have this. Okay. Now it's much easy to understand. So you have mu2 here and I5. And then you have these two branches which are like that. So that's okay. One branch is connected to mu1 here, and one other branch is here. And then you do the same for mu1. You have mu1, which is I3 here, and these two branches will go outside, so it's okay. It's exactly the reformulation of that using the previous natural transformation and the notation mu tilde. It's exactly the same thing. There is no problem. Okay. So now, so this is equal to that is unchanged. So equal to that times, let me write it here. This is equal to this part which is unchanged times another diagram for this one, which will be exactly the same idea. So so mu4, mu3, 1, 2, 3, 1, 2, 3. mu4, mu3 with a tilde now. And let me draw it. So now you have this one here, this one connected like that, this one, and this one. What was the color for the I5, I6 here, I1, I2, I4, I2, I4, I2, I4, okay, I1, you see I1, I2, I4, I1, I2, I4, and I5, etc. And you can check as an exercise if you like. But this is what we get here is exactly like that, so no problem. It's okay. Okay. So if I want, yeah, should I write it in a single line? Maybe not. Yeah. Let me keep it like that. Okay. So this is okay for equation 13. Now, what do we want to do? Okay, so now you have a sum here. You have a sum, and the goal here is to isolate this coefficient. So to isolate this coefficient, we will multiply, we will compose this picture by the dual of this one. This one, this single one. So we will, in some sense, we will put that, we will rotate here, and then the goal of that is when you will do this, when you will compose with a dual like that, you will here only keep one summand, the summand for a single coefficient. And here you will have a picture which will be equal to this summand up to some constant, multiplicative constant, we will explain. And then that will provide, in fact, the exact monoidal tetrahedron corresponding to the F symbol as defined in the section for Pentagon equation. So, next, by applying morphism from, and here we need to apply the right dual, the right. So before we consider the left dual, but in fact it is exactly the same idea. From right dual basis, and I hope we don't need, because here I wrote with left dual. So I am wondering whether we should write with right dual maybe here. Anyway, you can put left and right dual if we need, because we will apply that for fusion category, which is rigid, so no problem. By applying morphism from right dual basis, so we will use the notation this notation for the right dual. So the bijection for the usual bijection. I see. Maybe I understand what I mean, because remember that what we call the dual basis is not the dual in the sense of the category. This is dual in the sense of vector space. That's why this one is not what we call that, or what we called that also before. This is not the left, or this is not the right dual in the sense of category of the morphism. This is in the sense of vector space. So that's why maybe there is no problem to consider only the left dual category with left dual here, because here it's in the sense of category, whereas here is in the sense of vector space. So it should be okay. Okay. And so the goal of applying such morphism, as I explained, is to vanish the right-hand side summand except one, so that we will keep a single summand, and we will provide a formula for that pictorial. Okay, so let me do that here. Okay, so you get, so we will multiply this, as I said, we will, okay. So next, by applying morphism. So we will do, it's not just applying morphism, but it's Then it's doing some inner. There is what we call the bilinear form. So we will apply the bilinear form. So maybe I should specify. So bilinear form. Bilinear form. Here. Okay, so next by applying morphism from right dual and bilinear form, and the usual bilinear form, and the usual bilinear form, we get. So I did not write that in the paper. I will add it, but I have no time to write now the correct formulation, so I just write it like that. We get something like that. So you have, okay, so let me repeat. So you have mu1, mu2. So let me, so maybe I just need to copy and paste that, but maybe a problem. Okay, so you get something like that. So let me write it. 1, 2, 3, 4. So I am writing too big. Anyway, here the color is orange. So you have the picture before, this one and this one. But here also you apply the right dual of the one on the right. So this is something as follows. Let me write it and then I will explain a bit how it comes from. So this is the same as before, like that. Here you have like that. So go to this one. This one go here. So you just apply the usual bilinear form. There's no mystery. Like that and like that. And the last one is as follows. Okay. So you recover that. This is doing like that because this is the bilinear form. Remember, the bilinear form is something like that. You are doing something like that. So you have this component like that. Then here, so you have these 3 I1. So I1 is here. I2, I3. So I2 is here, I3 is here, if I'm not mistaken. No, I2, I4. Anyway, so you consider the right dual of that, which is something like that, and then you apply the bilinear form. And you get something like that. And this will be our F symbol up to a multiplicative constant. But on the right-hand side, you will get something which is 0, except for 1. So let me write it. The summand, which is non-zero. So it's equal to so equal to the same E1, E2, E3, I4, I5, I6, mu1, mu2, mu3, mu4 times something similar. Let me write it like that. And now you will have only mu3 and mu4 here. So so you have mu4, mu3 as before, and the right dual, and they composed as follow. So it's an exercise to see how it should compose. I do not detail here. So this one go here. This one go here. This one go here. Okay. This one here. This one here. And like that. Okay. So and the morphism are, so let me write few morphism. So you have I5 here, for example, I3 here, etc. You have I5 here, I6 here, etc. Okay. So this so the F symbol is that up to this constant, which will be more or less be given by just a dimension. So okay. So then so you recognize here the monoidal triangular prism up to some zigzag relation. So you need to move a little bit some boxes, and you will identify exactly the reference pattern of a monoidal tetrahedron. So then, by some zigzag relation, relations, and the fact that from C1 X I6 tensor X I6 star is one-dimensional, is of this form. So it's generated by this morphism, co-evaluation map. So we have that. Then, so what I mean by that here, so why I am considering that from 1 to I6 tensor I6 star. So I6 is here, and I6 star is where? This should be I6 star. You have something here. Okay, so that what I am doing here is that can be replaced. So you have 1 and I6 star. That can be replaced by a co-evaluation map up to a constant. So that can be replaced by something like that. You can replace everything by that, up to a constant. And then by zigzag relation, what you get here is only this one, and 3 branch like that, up to a constant. And this constant will be some dimension. So you get the monoidal tetrahedron. So I guess it's so you get the following: the monoidal tetrahedron. But I don't go into too much details here. Maybe an exercise to identify like that, but it's very easy. Equal. So this corresponds to that, up to some zigzag relation. So I will continue after the pause. Monoidal tetrahedron. Equal something, we will explain after the pause. Pause. We can restart. Okay, so up to some zigzag relation, this picture is exactly the monoidal tetrahedron, as we explained in the first sections. So be careful, you need to put, for example, some row natural transformation we defined before, but up to that, it's okay. So we have that. And we have this here. And it remains. So the constant coming from here. So this is, I said, this is that up to a constant. And in fact, this constant is the dimension of I6 inverse. Dimension of I6 inverse. di6 inverse. And so it's an exercise also to show that it is that. And you have what remains from the picture on the right-hand side. You have something like that. mu4 like that. Okay. So, and this is, so you replace this by the constant, and this here is by definition of the radial, this is 1. So what you get is that equal to that times di6. So let me write it like that. Exercise. It follows that So this equal di6 of this. Okay. Okay. Now we want to reformulate. So now we have the formula for the F symbol in terms of monoidal tetrahedron. So we can reformulate the Pentagon equation here. So let me do as before. I will copy and paste. It will be more easier to understand. So now we can reformulate Pentagon equation 14 as follows. So this is just as follow. Okay. So you just replace every F symbol by that. Here, 1, 2, 3, 4, 5. So you will have this monoidal tetrahedron, but this multiplicative constant also. But let me write here that you will have di1, di6 factorizing on the left-hand side and on the right-hand side, which are, so di1, di6 are non-zero, so you can simplify. di1, di6. So the coefficient is the coefficient of this one here. I1, I6, I6, I1. So the one coming from that and from that can be simplified. It only remains di0. di1, di6 factorize on left-hand side and right-hand side. So can be simplified. Okay, so mu 0. We have the sum. Ah, yeah, so now it's quite boring. So it's just a reformulation of mu 6, mu 5, mu 0 t. Okay, so maybe let me see. Can I copy and paste something? Maybe I can do that. It will be here. It will be quicker, but I will have to change the indices. So let me copy and paste that. 1, 2, and 1, 2, 3. 2. I have no place. Okay. Let me write it smaller. 1. 1, 2, 3. Okay. Okay. And we have to change the indices everywhere. So 4, 6, 5, 0. 4, 6, 5, 0. Then 1, 0, 2, 3. 1, 0, 2, 3. Then 7, 5, 2, 8. 7, 5, 2, 8. Yes, I should have copied the blank pattern. 9, 6, 8, 3. 9, 6, 8, 3, 4, 9, 7, 1. Okay, and as I said, you have an extra one of the dimension. So this one, I0, do not cannot be simplified, so you have to add it here, the I0, and you have the sum over I0 and mu7, mu8, mu9 in the corresponding basis. Okay. That's okay. Now you can reformulate. So now you have you have this equality, which is not yet the triangular prism equation. We can write it using the more symmetric tetrahedra and the reference pattern, what we call the definition 8.1. So then, following definition 8.1, we get, so 8.1 is the reference pattern for the reference pattern for that. We get the following. So this is the same. Okay. So now the goal is to write very, I have an idea. To write very cleanly. I will write 1. And then I will copy and paste this. Like that. So copy, paste, and now no. Here we make it small. Now I have place for 5. So sum 1, 2, 3, 4. Okay. Then we need the orientation. So now you just apply the reference pattern. So I was stupid. I must, so I will erase because the orientation is the same everywhere. So I have to copy also the orientation. So this one, this one, this one, like that, and like that. Okay. So now I can copy that. And I will copy also, yeah. I will also put the mu, the blank mu, because the same everywhere also. So mu, here. Mu, like that. And inside it is row inverse of tilde mu tilde of something. And I will gain a lot of time like that. Here, tilde mu, like that. Okay. One, two, one, two, 3. I need a bit more space here. So I am almost done. Huh? I am almost done. Here. Okay. Okay. Now, here you have equal the sum I0, mu 7, mu 8, mu 9, di0. And here the sum for mu 0. And the indices. So 5, 6, 0, 4, 1 here, 7, 2, 2, 8, 7. So this one should be 8, if I'm not mistaken. 9, 4. I will check something. 0, 3, 5, 8, 6, 3, 9, 1. So I have a doubt about this one. So the second equal. Yeah, it's okay. It's this one. 9, 4. This is 9. So wait, no, this one. No, it's a 7. Okay. So my doubt was 7 here. Anyway, doesn't matter. Just need to report the good indices coming from the previous equality. You get something like that. Okay. So maybe I can move. Okay. So this is the first step. Now we want this to look like the usual development, but to be as close as possible of the usual development of the usual triangular prism equation. This is not a triangular prism equation here, because the labeling is not the labeling of a triangular prism equation, but we can make it as close as possible. 7, 9, 4. Okay. Okay. So this is okay. So let me write now that. I will go very quickly because it's not very interesting. So from now, so each step of the following is left as an exercise. Otherwise, it would be too boring. So now you apply by what we call rule 1. So remember what we call the rule 1 was, remember you have a series of rules. I don't remember, you have I, and you can replace it by something like that. You change, I don't remember. Anyway, something like that. The rule to change the corner. So we will change the corner somewhere. I guess maybe you have something, and then you change a corner you don't have, etc. This rule play with the natural transformation rule. So I can change the corner everywhere here. Here, 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 and here. And I get the following. So it's not complicated. I will just have to copy and paste that and change the one corner. If I can. Okay. Okay, hope you get that. I hope I did not miss something. And now you change the corner everywhere you need. So you change the corner, every corner in the middle. So you apply the rule 1, 1, 2, 3, 4, 5 times. And you get here mu 4 t right, mu 1 t right, like that, mu 7 t right, mu19, right? And mu4 till right. Okay. Now we will apply some 3D move. Then, by applying proposition 8.5, so this proposition is about 3D move. 3D moves. We get the following form. We get the following form. Yeah. And now I am too it's too boring. So let me see how I can do. So in fact, this one will go here, this one will go here. So let me see what I can do. I will copy from the paper because it's too boring. Where is it? This one. I will take from here. And okay. I will put it directly here. No. Not that. This one. Okay. Okay. We get that. It's much easier to do like that. Okay, so be careful. This one go here. This one go here. So it's okay. I don't need to do it. This one is here. This one is here, and you have the move, 3D move. So for example, 8, 9, 6, 3. This one is here. This is not the 3D move. And now this one corresponds to this one up to some 3D move. So it's an exercise. As I said, it's left as an exercise. Just to avoid any confusion, this one is a 3D move of this one is a 3D move of this one, etc. This one is a 3D move of you can reorder here because it's just number, it's a multiplication of numbers, so there is no problem. This one is here, and this one corresponds to that, up to some 3D move. Okay. Okay. Finally. So, 3D move. Next. by applying rule 1 and rule 2 several times, we can recover the pattern of the reference pattern. So next, by applying rules 1 and 2 several times, we can put the label in the same corner than in theorem 810. The same corners than in theorem 810. So the theorem 810, what we call, remember, the simplified triangular prism equation. Simplified triangular prism equation. And I will do as I did. Now I will copy and paste from the paper directly. Get the following form. So which one? This one. Here. Okay. Ah, no. Ah. Okay. So be careful. So here the notation are not very convenient, not that convenient. So be careful that. So here. So now, okay. So we move that here. We get that, etc., etc. So there is no confusion here. It's okay. There is a confusion here. So this corresponds to this corner. This corner, this corner, this corner, this corner, this corner. In particular, this one, which is very long, is a morphism of this corner. So this is, yeah, maybe, I don't know. So I wrote it like that in the paper, but it's very ugly, very, very ugly. So maybe I should, I don't know. I should put a dot and an arrow, and I don't know, I should put a symbol maybe. And like this symbol alpha equal that, beta equal that, I don't know. But anyway, there is no confusion because it is supposed to be the same corner as this theorem. And we know that in this theorem, this is this corner which are considered. So that there is no confusion. And also this corner, etc., etc. So remember that the rule 1 involves this is just change the corner. The rule 2 involves row. Rule 2 is something where you put a pivotal structure. Anyway, so you get this equation. So we are closer and closer to the triangular prism equation. Now we have the good corner. The goal now is to remove as much as possible the natural transformation rho and sigma And in fact, we will not be able to remove it completely. The change of basis will keep a bit of this natural transformation, but we will see then that we will remove it in the TP up to moving a bit the label again. This will be what we call the TP configuration. Okay, so now observe that. So I leave it as an exercise. So the left dual of the right dual is the right dual of the left dual in the sense of is an identity in the sense of vector space, as I said before. And this, so you have to refer to the first section, I don't know, section 1 or 2, where we define this. I don't want to go into the details here. So the double categorical dual of the right dual of alpha is the left dual of alpha. And the double categorical right dual of the vectorial left dual of alpha is the vectorial right dual of alpha. Okay, so exercise. Okay, then we have row of, for example, of that. How to do with that? This is row inverse, row power -2 of row power 3 of that. It's okay, 3 minus 2 is 1. But this is, remember that this is nothing but the double left dual. We saw that. Remember, row is something like that. So 1, 2, 3, this is the double dual. So row inverse power -2 of that. But if we apply the previous exercise, you get that it is you can replace the right dual by the left dual. Row power -2 of something like that. So be careful. Now you have here, it's here and now here. Okay. Okay, so we will use that. Next, so remember that the theorem 8.10 has some assumption. So now, under the assumptions of theorem 8.10, we have, so let me check, I have a doubt here. Yeah. So we have the square of, so if you have the application of 2 times the pivotal structure is the identity. Okay. So if you apply the lemma 2.13 and 2.5, so let me recall the picture of this lemma. This one is, remember, it is a lemma looking like that. You have that equal that. You go like that. Equal something like that. And this dot is sorry. This dot is just the pivotal structure. This is equal something like that. Pivotal structure, tac, like that. Okay. So this is lemma 2.13. And lemma 2.5 is this lemma is something like that. You have something, a pivotal structure here, and it is replaced by something like that. So we move the pivotal structure from left to right up to doing some modification. So you put some inverse, I don't remember. That's why I don't put the same symbol, but up to applying these two lemma, we get that these two lemma, and this we get the following. So rho inverse of alpha like that equal. So this is identity. So wait, now I'm lost in my thing. Rho inverse. So I leave it an exercise, I don't remember the details. Something like that equal something like that. Exercise. The goal is to, using the previous lemma and all what I did before, this can be written like that. Exercise. Okay. Okay. And then, so you have that. So using this relation, and maybe also this relation, and this relation, we can simplify. So, in fact, yeah, I don't really remember in details why we need that, but it's very technical, so it doesn't matter. So we will be able to we will replace here here we will be able to put the because in the reference pattern here it's the left dual, here it's a right dual, and this is not good because we want the left dual for the reference pattern here because it corresponds to this one and this one. That's why we need to do such technical thing to be very close to. Okay, so you get then by applying the rules we get again something. So I will do the same thing here. I get that. Okay. We get that. So let us check. And we will finish tomorrow. So we will have no time to state the change of basis, but we will do that tomorrow. So here, let us check what kind of changement. Here we have here. So be careful now, you have this. Whereas here it's there. It was there, like that. So we apply some of the rule to get that. And I guess we apply something else, I don't remember. Or we can. Let me check here if it is. So we have that. And we can see some difference. It's only for the 7. Ah, yeah. I see some difference also here. We change, we apply. So here we have this, and by the small result we stated, we have no more this. Where is it? Here, no more these 2. Anyway, so we arrive here. And so we will finish tomorrow. So tomorrow, so it remains 3 lines. I will finish tomorrow because the time is over. And they may have another course by someone else. Let me say just orally that we will finally, so it remains 3 lines. We have to adjust the orientation. So we are almost done, but some orientation are not correct. So we will have to change the orientation by applying some natural transformation like that. But in fact, we will need to generalize it because this one applies only on the 3rd branch. But we will want to generalize it for one for each branch. So one for the 1st branch to put the pivotal structure, or for the 2nd branch, or for the 3rd branch. And when you do that, then you can change all the orientation as we need to be very close to the triangular prism equation, to be exactly the triangular prism equation, and then you can collect everything to get the exact change of basis. And finally, we will see tomorrow that you can simplify the TP to get the pentagon configuration. Okay, so that will not be so long. It's only 1 page. That will be done tomorrow. So end of session for today. So you can stop.